All right, welcome to Next Gen Manufacturing. Today, we're diving into some truly incredible materials that are literally shaping our future. And we're going to uncover the surprisingly clever fix for one of their biggest, and I mean biggest, hidden weaknesses.
So let me ask you this. How is it even possible for a material to be as strong as metal, but at the same time, as light as plastic? It really sounds like something straight out of sci-fi, doesn't it? But, this question is at the very heart of modern engineering. We're talking everything from Formula One cars to the jets flying way over our heads. And the answer, well, it lies in a special class of materials that are a total game changer.
And those game-changing materials, they're called composites. Honestly, they are the unsung heroes behind so many of the high-performance products we see today. So let's get into it. What exactly is a composite material?
At its core, you can think of it like a team effort. You take a binding ingredient, which is called the matrix, and then you fill it with these super strong reinforcements like tiny fibers or particles. When you mix them together, you get a new material that is way, way better than either of its parts on their own. It's kind of like reinforced concrete, but on this incredibly advanced, almost microscopic level.
And this is exactly why composites are so popular. It means engineers can essentially cherry-pick the absolute best traits from totally different materials. They can design a single material that gives them the anvil-like strength of metal, the feather-light weight of plastic, and even the rock-solid rigidity you'd expect from ceramics. It's the best of all worlds, all rolled into one. And because of these amazing properties, you find composites everywhere that performance is absolutely critical. Think about aerospace, right? Every single ounce you can save on a plane means massive fuel savings. Or high-performance automotive. We're talking race cars. And yeah, even in the sporting goods you might have at home, like high-end tennis rackets or super light bicycle frames. But, and this is a big but, these wonder materials have a hidden vulnerability. There's a problem that can pop up during manufacturing that's so serious, it can totally destroy the whole reason for using composites in the first place. This is what's known as the delamination dilemma. So what is delamination? Well, since a lot of composites are made from these thin sheets layered and bonded together, the force from a cutting tool can actually peel those layers apart. Imagine trying to separate the pages of a book that have been glued together. And this isn't just a little cosmetic flaw. Oh no, it's a serious, catastrophic structural failure. The stakes here are just enormous. Just picture a multi-million-dollar component for a new satellite or a fighter jet. If just one single hole is drilled incorrectly and it causes delamination, that whole part might have to be tossed in the scrap heap. The cost of one tiny little error can be absolutely massive. It's kind of crazy. So why does this even happen? Well, the investigation leads us straight to the tools themselves. It turns out that the standard tools that are designed for cutting metal are pretty much the worst possible choice for these layered composites. Okay, so here's the real heart of the issue. A standard cutting tool has these spiral grooves, they're called flutes, and they all go in one direction. And what that means is they either pull the material up or they push the material down. And for a layered material, trust me, both of those options are very bad news. So if you use an upcut tool, its flutes spiral up and they yank on the top layers, causing them to peel away. Delamination on top. Okay, so use a downcut tool, right? Well, that one pushes down so hard that it blows out the bottom layers. Delamination on the bottom. You see the problem? Either way, you get delamination. You just can't win. So if pushing up is bad and pushing down is also bad, what's the solution? This is where a little bit of brilliant engineering comes into play, with a tool designed specifically for this exact problem, the compression cutter. The big idea is actually pretty simple, but it is revolutionary. Instead of trying to pick between an upcut and a downcut force, what if a tool could do both at the exact same time? And that is the whole principle behind the compression cutter. And here's how it works. It's so cool. The top half of the cutter has flutes that are pushing down. The bottom half has flutes that are pulling up. So when the tool is cutting through the material, these two opposite forces meet right in the middle. They effectively pinch or compress the layers together, holding them perfectly stable while the cut is being made. And the result? A perfectly clean edge. No delamination on top, none on the bottom. It's just an incredibly clever and elegant design. This solution really highlights a fundamental rule in advanced manufacturing. Choosing the right tool for the job isn't just, a good idea. It's an absolute necessity. The design of this one small cutting tool has massive, massive implications for the entire industry. So ultimately, by using a compression cutter, manufacturers can prevent that costly delamination, they get a perfect finish, and, this is the big one, they save those incredibly high-value parts from ending up in the scrap heap. This single tool choice is what makes it possible to reliably use these amazing advanced materials in the first place.
Now, there is one last really important detail. This tool is a specialist. Its unique geometry is designed specifically for cutting along the edge of a part. That's an operation called profiling. It's not meant for, say, plunging straight down to make a hole. It just goes to show for every specific task, there's a specific, optimized solution out there.
And that really leaves us with a fascinating question to think about. We've just seen how the simple geometry of a single cutting tool can make or break a multi-million-dollar component. It really makes you wonder, what other seemingly simple choices in tools, in software, or processes are quietly defining the entire future of next-generation manufacturing?